For 96 years, a concrete wall in the middle of the Arizona desert did something almost impossible to picture until you actually stand there and see the empty stream bed for yourself. It took nearly every single drop of water from a creek that had been flowing uninterrupted for thousands of years, and it diverted every bit of it into pipes, sending that water toward turbines instead of down the natural channel that desert plants, fish, and entire ecosystems had depended on since long before anyone thought to build a dam there at all. For nearly a century, this wasn't just a diminished river. In long stretches, it was barely a river at all. Then, one afternoon in 2005, the engineers pulled the switch, closed the diversion, and let the water flow back into the original creek bed for the first time in almost 100 years. What happened next became one of the more closely watched natural recovery stories in the American Southwest, a real-time experiment in whether a desert river, silenced for generations, could actually remember how to be a river again. To understand why this story matters, and why researchers have continued studying this specific stretch of water so closely in the decades since, you first need to understand exactly what Fossil Creek is and why it was considered valuable enough to dam in the first place more than a century ago. Fossil Creek is a perennial desert stream, meaning it flows year-round rather than drying up seasonally, located in central Arizona, cutting through the rugged landscape of the Verde Valley before eventually joining the larger Verde River. What makes Fossil Creek genuinely unusual, even by the standards of desert waterways, is its source. The creek is fed primarily by a series of natural springs, releasing a remarkably consistent flow of mineral-rich water that emerges from the ground at a nearly constant temperature and volume, regardless of the broader seasonal drought conditions that dominate so much of the surrounding Arizona landscape. This specific mineral composition, heavy with dissolved calcium carbonate, is responsible for one of Fossil Creek's most visually striking natural features, travertine, a form of limestone that forms when mineral-saturated spring water is exposed to open air, causing dissolved calcium carbonate to precipitate out and gradually build up into hard, layered deposits. Over time, and specifically over very long spans of time, this process naturally sculpts a landscape of stepped terraces, natural dams, cascading pools, and turquoise-tinted swimming holes, a genuinely striking, almost otherworldly landscape that looks considerably more like something found in a tropical rainforest than in the middle of the Arizona desert. It was precisely this consistent, reliable flow of water that attracted engineers in the early 20th century, well before anyone was thinking in terms of environmental conservation or ecosystem preservation. Beginning in 1909, Fossil Creek's water was diverted to power the Childs and Irving hydroelectric facilities, a pair of power plants built specifically to take advantage of the creek's dependable flow, generating electricity for the growing communities and mining operations scattered across this region of Arizona during a period when reliable electrical power was still a genuinely valuable, scarce commodity across much of the American West. To make this diversion possible, engineers constructed a dam directly across Fossil Creek, redirecting the overwhelming majority of the stream's natural flow away from its original channel, and into a series of pipes and flumes that carried the water toward the hydroelectric turbines instead. For the better part of the following century, this arrangement remained essentially unchanged. The dam continued diverting the vast majority of Fossil Creek's water, year after year, decade after decade, while the original stream bed below the diversion point was left with only a small fraction of its natural flow, nowhere near enough to sustain anything resembling the thriving, travertine-rich desert ecosystem the creek had supported before the dam was ever built. By the closing decades of the 20th century, the calculus around this arrangement had begun shifting considerably, driven by a combination of factors that eventually made continuing to operate these aging hydroelectric facilities considerably less compelling than it had once been. The infrastructure itself was aging, requiring increasingly significant investment to maintain safely and reliably. At the same time, growing scientific understanding of the ecological value of undammed desert streams, combined with the Fossil Creek watershed's unusual biodiversity and its significance to several indigenous communities in the region, including the Yavapai Apache Nation, added considerable additional weight to the case for reconsidering whether these aging power facilities were still worth operating. In 2005, Arizona Public Service, the utility company operating the Childs Irving facilities, made the decision to decommission the power plants entirely, shutting down the diversion and allowing the full natural flow of Fossil Creek to return to its original stream bed for the first time in 96 years. This decision carried genuine historical significance well beyond just this one specific creek. According to documented records of dam removals across Arizona, the restoration of Fossil Creek's full natural flow marked the first time a desert stream in the entire southwestern United States had been restored to its natural flow in this way, following the decommissioning of hydroelectric infrastructure that had diverted it for generations. It was also, more broadly across the entire country, only the second time in United States history that A dam had been removed specifically and primarily for environmental reasons alone, following the well-documented 1999 removal of the Edwards Dam in Maine, a landmark case in the broader ongoing history of American dam removal and river restoration efforts. Notably, unlike the Edwards Dam situation, which involved fish species with real commercial and recreational significance, driving much of the public and political motivation behind that earlier removal, the case for restoring Fossil Creek rested almost entirely on ecological and cultural grounds, supporting native fish and wildlife species with comparatively little commercial or recreational value attached to them, a detail that speaks to a genuine values-driven shift in how conservation decisions were increasingly being approached by this point in the early 21st century. The actual physical removal process for the dam itself unfolded somewhat gradually, rather than happening all in a single dramatic moment. In 2005, when the power plants were formally decommissioned, the full flow of water was returned to the creek, even though the physical dam structure itself remained largely intact at that point. It wasn't until 2008 that the top 6 feet of the dam were actually physically removed, while the remainder of the structure was deliberately left in place, a decision made specifically to help manage overall project costs, and notably, to serve a specific, intentional ecological purpose, blocking the upstream passage of invasive fish species that had established themselves in portions of the watershed during the decades the creek had operated under diverted, artificially altered flow conditions. This detail is worth pausing on because it illustrates something genuinely important about how modern dam removal and river restoration projects actually work in practice. Removing a dam isn't simply a matter of tearing down a barrier and walking away. It often involves careful, deliberate engineering decisions about exactly how much of a structure to remove and in what configuration, specifically to maximize ecological benefit while managing genuinely complex trade-offs, including, in this particular case, preventing invasive species from spreading further upstream into habitat that native, more vulnerable fish species depended on. So what actually happened once the water returned to Fossil Creek's original channel? This is where the story becomes genuinely scientifically compelling, because the recovery that followed didn't unfold as any kind of instant, dramatic transformation. Researchers who have studied this restoration closely in the years and decades since have been consistent and clear on this specific point. Fossil Creek's recovery did not produce an instant return to some perfect, pristine, prehistoric condition. Instead, the river adjusted gradually, step by step, over an extended period of time, and it's precisely that slower, more methodical, genuinely observable recovery process that became the real scientific story here, considerably more valuable to researchers than a simple instant before and after comparison would have been. To understand why this gradual, incremental recovery process carries such genuine scientific value, it helps to walk through exactly what actually needed to happen once Fossil Creek's full natural flow was restored. Because a river isn't simply a passive channel that either has water in it or doesn't. It's a genuinely dynamic system, and restoring its water flow set off a whole cascade of interconnected physical and biological processes, each one unfolding according to its own particular timeline. With full flow restored, water once again began moving sediment through the channel in the way it naturally would have before the dam was built, gradually reshaping the physical structure of the stream bed itself over time. The mineral-rich spring water, no longer diverted away through pipes and flumes, once again began releasing its dissolved calcium carbonate directly into open air along the natural channel, allowing researchers to observe in genuinely real time the same travertine-building geological processes that had originally created Fossil Creek's distinctive terraced pools and cascades, processes that had been almost entirely interrupted for nearly a full century while the water had been diverted elsewhere. Pools throughout the creek gradually changed shape as sediment movement and renewed travertine deposition continued reshaping the channel bit by bit. Plant communities slowly began colonizing the recovering stream bed and surrounding banks, reestablishing vegetation that depended on the kind of consistent water access the creek's restored flow now provided. And aquatic communities, the fish, invertebrates, and other organisms living directly within the water itself, gradually responded to this changing, recovering habitat, adjusting their own populations and distribution patterns as conditions within the creek continued shifting and stabilizing over the years following the restoration. None of this, researchers have been careful and consistent in emphasizing, followed any kind of simple, predictable timetable. This is genuinely part of what makes Fossil Creek such a scientifically valuable, closely studied case within the broader field of river restoration ecology. It offered researchers a rare, genuinely well-documented opportunity to observe exactly how a spring-fed desert river actually responds when one of the single largest human influences on its natural flow is removed, watching that recovery unfold organically over years, rather than trying to reconstruct or model it after the fact from incomplete historical records. It's worth explaining a bit more about why this particular kind of desert stream restoration carries such distinct scientific interest compared to river restoration projects happening in other, less arid parts of the country. Desert ecosystems operate under genuinely different constraints than the wetter, more temperate environments where a considerable amount of river restoration research has historically been conducted. Water in a desert environment is an extraordinarily precious, limiting resource, shaping essentially every aspect of the surrounding ecosystem structure and function in ways that simply don't apply in the same way to a river restoration project happening somewhere with abundant, consistent rainfall throughout the year. A desert stream like Fossil Creek, fed by consistent spring flow rather than relying primarily on seasonal rainfall or snowmelt, represents a genuinely unusual, valuable natural laboratory for studying exactly how aquatic and riparian, meaning streamside, ecosystems respond and rebuild themselves when water access is restored, offering insights that researchers studying river restoration in wetter climates simply can't obtain from their own differently structured systems. This broader research value connects directly to why Fossil Creek's story carries genuine relevance well beyond just this one specific creek in central Arizona, extending into the much larger, ongoing national conversation about dam removal and river restoration happening across the United States more broadly. It's worth being clear and honest that the lesson researchers have drawn from Fossil Creek's recovery isn't a simple, sweeping conclusion that every dam is inherently harmful, or that every dammed river should automatically be returned to some earlier undammed state. Dams provide genuine, substantial benefits in many parts of the world and across many different specific circumstances, including water storage for drinking and irrigation, flood control protecting downstream communities, and electricity generation supporting entire regional power grids. The more nuanced, considerably more useful lesson that Fossil Creek's carefully documented recovery actually offers is this. Removing a dam represents only the very beginning of a considerably longer, more complex ecological process, not the completion of one. Once a dam structure is physically gone, the river itself has to do the rest of the work, gradually, through its own internal, physical, and biological processes, rebuilding a functioning ecosystem piece by piece, on its own particular, genuinely unpredictable timeline, rather than snapping back instantly into some idealized, fully restored condition the moment the physical barrier disappears. This pattern, where the actual ecological recovery following a dam removal unfolds gradually rather than instantly, isn't unique to Fossil Creek specifically. It's been documented across numerous other dam removal projects throughout the United States, and looking at some of these other cases helps place Fossil Creek's own recovery in a broader, genuinely useful context. When the 45-foot Marmot Dam was removed from Oregon's Sandy River back in 2007, nearly 1 million cubic yards of sediment that had been steadily accumulating behind that dam for 90 years cleared itself out of the system in less than 2 years following the dam's removal, a genuinely striking demonstration of just how efficiently a river can naturally process and redistribute even an enormous accumulated sediment load once it's given the physical opportunity to do so. Industry professionals who specialize in planning and managing dam removal projects have specifically noted that public perception often remains a genuine ongoing challenge in these situations, since many people understandably worry that removing a dam will simply leave behind some kind of permanently degraded, unsightly mudflat rather than a genuinely recovering natural ecosystem. The accumulating body of evidence from actual completed dam removal projects, Fossil Creek very much included, has increasingly demonstrated that most rivers, when given the chance, actually do return to a genuinely healthy, functioning condition relatively rapidly on their own, though, as Fossil Creek's own carefully studied recovery has shown, rapid in this specific ecological context still generally means a process unfolding across multiple years, rather than happening instantaneously. It's also worth understanding a bit more about the practical, logistical side of how dam removal projects like this one actually get planned and executed, because the process involved is considerably more involved than simply deciding one day to tear a structure down. Professionals working in this specific field generally describe a fairly standard multi-year process for even a comparatively small dam removal project. The first year typically involves initial reconnaissance work, carefully assessing the specific dam and surrounding watershed, alongside the often lengthy process of securing adequate project funding. The second year generally involves detailed engineering design work, along with the process of obtaining all the various required environmental and regulatory permits, while fundraising work often continues simultaneously. Only in the third year does the actual physical removal work typically take place. This extended methodical planning timeline reflects the genuine complexity involved in safely, responsibly removing a dam structure, particularly one that's been in place for as long as Fossil Creek's diversion dam had, without triggering unintended, potentially harmful downstream consequences during the actual physical removal process itself. There's a specific engineering approach worth understanding in a bit more detail as well, because it directly connects to why Fossil Creek's own recovery process unfolded the way it did. Dam removal projects generally follow one of several different possible physical removal strategies, each carrying its own distinct trade-offs. A notch and release approach, considered by many restoration ecologists to carry the strongest overall ecological benefits, despite being a comparatively slower process, involves gradually draining the reservoir behind a dam through a series of carefully cut notches, allowing water, and critically, the sediment that water carries, to flow out of the system at a consistent, carefully managed rate rather than all at once. This measured, gradual release allows the downstream ecosystem considerably more time to adjust to the resulting changes in water flow and sediment load, rather than facing an abrupt, potentially overwhelming surge all at once. This general approach, prioritizing a more gradual, ecologically sensitive removal process over the fastest, cheapest possible method, reflects the same broader philosophy that shaped how Fossil Creek's own dam was ultimately handled, with the decision to remove only the top 6 feet of the structure while deliberately leaving the remainder in place, specifically to help manage invasive species concerns, representing exactly the same kind of careful, deliberate engineering trade-off. Stepping back from the specific engineering and ecological details, it's worth considering what Fossil Creek's story actually reveals about the broader relationship between human infrastructure and the natural systems that infrastructure inevitably alters, sometimes for the better, sometimes for the worse, and often, as this specific case demonstrates, in ways that can genuinely be reconsidered and meaningfully reversed decades later, once circumstances, priorities, and scientific understanding have all evolved considerably. For 96 years, a piece of early 20th century engineering built to solve a genuinely real and pressing problem at the time, generating reliable electricity for a growing, developing region of Arizona, fundamentally reshaped an entire desert ecosystem, reducing what had once been a thriving, travertine-rich perennial stream down to little more than a diminished trickle for nearly a full century. And yet, once the specific circumstances that had originally justified that diversion, primarily the ongoing need for exactly this specific source of hydroelectric power, had genuinely shifted, the decision to reverse course and restore the creek's natural flow proved both technically achievable and, based on everything researchers have documented in the years since, genuinely ecologically successful, even though that success unfolded gradually, through years of patient, incremental recovery, rather than through any single dramatic, instantaneous transformation. This raises a genuinely interesting, broader question worth sitting with for a moment. How many other dammed rivers and streams scattered across the American Southwest, and indeed across the broader United States as a whole, might similarly be candidates for this same kind of careful reconsideration? As aging infrastructure continues reaching the natural end of its practical operational lifespan, and as scientific understanding of the genuine ecological value tied up in restoring natural stream flow continues to grow and deepen, Fossil Creek doesn't offer a simple, universal answer to that broader question. And researchers studying this specific case have been consistently careful not to overstate what one successful, well-documented desert stream restoration necessarily implies for every other dammed river facing its own particular, genuinely different set of circumstances. What it does offer is a genuinely valuable, carefully documented real-world case study, a functioning, living example of exactly what can happen when a desert river is finally given the physical opportunity to reclaim its own original channel and rebuild its own ecosystem, largely on its own terms, and according to its own particular, gradually unfolding timeline, after nearly a full century spent existing as little more than a diminished, engineered trickle. What makes Fossil Creek's continued significance genuinely worth appreciating, even now, roughly 2 decades after the initial 2005 restoration, and well over a decade since the dam's physical top section was finally removed in 2008, is that researchers have continued actively studying and monitoring this specific site, precisely because the gradual, ongoing nature of its recovery continues offering genuinely valuable scientific insight, even this many years later. A river doesn't simply finish recovering at some fixed, predetermined point, and then remain permanently, statically unchanged from that moment forward. It continues adjusting, continues responding to changing conditions, continues being genuinely shaped by the ongoing interplay between water flow, sediment movement, mineral deposition, and the plant and animal communities that depend on all of these interconnected physical processes working together. Fossil Creek, in this specific sense, remains an active, ongoing scientific story, rather than a completed, closed chapter. A desert stream that spent 96 years being told, through direct human engineering, exactly how much water it was allowed to carry, and that has spent the years since being carefully, patiently, and scientifically observed as it works out, gradually and entirely on its own terms, exactly what kind of river it actually wants to become, now that it's finally been given the chance to decide that for itself.